Okay, so thank you, Jasmine, once again for agreeing to come talk with us. It's really an honor for us to have you here. We really enjoyed your first talk, and we're really looking forward to hearing what you have to say for your second talk. So please take it away.
Awesome. Okay. Hopefully you see it kind of full screen now.
Looks great. Yeah.
And okay, I guess goes without saying also after the last talk, but please do interrupt me. And so I'm trying to make you guys a little bit bigger so that I can see if you raise your hands or something. Although I don't know how I did that last time. There we go. Okay, you're a bit bigger now. Yeah, so please do feel free to interrupt me. Definitely happy to have a lively discussion. So, all right, so last time kind of what I was sort of telling you about, to give a little bit of summary, is first kind of the main point that I wanted to make is that these objects called jets really give us kind of access to the kinematics of interactions in collisions of protons. And so they're a pretty powerful way to study how these types of interactions happen in proton-proton collisions. And in addition to kind of accessing the kinematics of this sort of hardest initiating parton, in some way you can also kind of look inside of jets and try to look in more detail about individual splittings that happened in the development of the shower. And this idea is sort of part of jet substructure. So what I kind of introduced last time is that I first wanted to talk about sort of jets as they're produced in collisions of protons, and this in many ways is kind of the simplest case. But what I really want to go towards, and what I'm particularly interested in discussing, is jets in heavy ion collisions, and in particular how these can kind of provide us a way to sort of access kind of information about the quark-gluon plasma produced in heavy ion collisions. So to give kind of a little bit of sort of backstory, which probably everyone is sort of familiar with, is that in heavy ion collisions really provide us kind of unique access to this deconfined phase of QCD matter. So the essential idea is that kind of at the LHC, for example, sort of in the collision of two large nuclei, you can really access a swath of this sort of low baryon density and high temperature regime of the phase diagram. So you undergo sort of a phase transition where sort of nuclear matter melts to form the quark-gluon plasma. And this quark-gluon plasma then sort of subsequently evolves and cools until it goes back through this phase transition to hadrons. And it's this sort of phase of QCD matter that at least I'm particularly interested in studying using jets. So there's a couple of what I would consider kind of crucial pieces of evidence which people sort of consider when they talk about the formation of the quark-gluon plasma in heavy ion collisions. So one is that sort of relatively low momentum particles produced in the collision have kind of characteristic correlations between them that imply sort of collective behavior, so that indicate that they experience strong interactions between one another that generate these sort of long-range azimuthal correlations. And these kinds of correlations are on relatively low scales, like kind of the order of the temperature of the plasma. But if you look on much higher scales, we also see a suppressed yield in heavy ion collisions of both jets, but also hadrons and other kind of hard processes from interactions with the medium. So this kind of is indicative essentially of strong interactions between these high momentum particles, which are produced in the kind of underlying collision and the quark-gluon plasma. So this is kind of the types of signatures which give us access to this interaction in heavy ion collision. I don't really go into like any details on my work. I want to really try to sort of give, hopefully, especially for the students, a little bit of an introduction of kind of what I see as the picture of the evolution of a heavy ion collision. So on relatively low scales, like around, say 1 GeV as an example, you can think of this like collision of nuclei as sort of like a collision of two pancakes of very high energy density, which deposits just enormous amounts of energy density in a kind of lumpy way in the point of the collision. And so kind of right after the collision, the system is super far from equilibrium. So you just have like lumps of stuff all over the place. But actually relatively quickly, within a half or 1 Fermi over C, depending who you ask, this very far from equilibrium state actually kind of undergoes sufficient sort of equilibration with the rest of the particles around it to bring it kind of close enough to equilibrium that you can describe sort of the subsequent evolution of this matter with hydrodynamics. And so from about 1 Fermi over C to 10 Fermi over C or so, kind of the evolution and expansion and cooling of this quark-gluon plasma is described by hydrodynamics until it sort of cools enough that it undergoes the phase transition again, and all of these particles sort of freeze back out and turn into hadrons. And then to kind of connect, I guess, to what I talked about last time, at the same time that all of this evolution of the quark-gluon plasma is happening, on much higher scales, you can also have these high energy interactions between like protons, for example, in the two nuclei that produce these much higher energy scatterings. So in some way, you can kind of think of the jets that we talked about last time as sort of providing some kind of probe or bullet through the quark-gluon plasma. So I like sort of the analog that if you want to, studying jets as a way to study the quark-gluon plasma in some sense is sort of like studying the deflection or the energy loss of this bullet in the apple to try to kind of access information about the structure of the apple and how it interacts with bullets. So that's kind of to try to put jets, which I talked about last time, in a little bit more of a picture of heavy ion collisions. At this point, do you guys have any like questions? Yeah.
I have one just about this now. So there's sort of two parts of evolution here. There's the quark-gluon plasma evolution, and then there's the jet that will sort of shoot through it. I was just curious, so the jet now branches off into a whole bunch of different particles. Is there eventually a point where the jet has split enough times that maybe some of the jet particles start to resemble the plasma and become sort of indistinguishable?
Yeah, that is an excellent question. And I think you're exactly right. So in some way, of course, these are all QCD interactions. So I'm kind of using implicitly this separation of scales between this sort of high momentum QCD parton and the lower momentum QCD partons, which are part of the medium. And so when there's that separation of scales, you can kind of think in some reasonably cohesive way about a difference between the high momentum parton, which is interacting with this low momentum parton. But then, as you said, as you get this excessive fragmentation, at some point, it's, I would say, probably not even well defined to say what particle kind of came from the jet versus, for example, like say that you have either you can have a relatively like low momentum particle from the jet, which, as you said, is like hard to distinguish from the medium, Or you can also have, some, what we would maybe think of as a particle from the medium, but which is hit so hard by a parton from the jet that it gets much higher energy. And to really like distinguish these in some way, I'm not sure is kind of meaningful once you don't have any more this separation of scales. So once you're talking about low momentum parts of the jet and relatively low momentum parts of the medium, I think it all gets really kind of mixed together. And that's, in the experiment, what they have to actually deal with is they have, of course, all of these particles all at the same time and try to isolate to the degree that they can the different effects.
Thank you.
Yeah. Any other thoughts, comments? Okay, awesome. Yeah, very good question. Cool. Yeah, so we want to use jets to try to study the quark-gluon plasma. And so I've been kind of talking so far about jets as these like kind of complicated extended objects where you have really many different particles. And that's kind of a more complicated case. But if you think about the case that you have just one parton, so like one quark or gluon in a finite temperature medium, then actually there's a fair amount of progress which you can make on trying to understand sort of the interactions of that parton with the medium and what kind of happens to it. And this was a lot of groundbreaking work already, back in the 90s. And kind of the sort of basic kind of conceptual idea, which is sort of all that I want to really try to convey here, is that if you have a medium of sort of scattering centers, then a high energy parton which is going through it is kind of going to basically undergo momentum diffusion due to sort of Brownian motion. So it will kind of go along and sort of acquire some kicks from the medium. And these tend to sort of broaden its transverse momentum. So whereas it maybe, was going in this direction, then through these interactions with the medium, and sort of acquires transverse momentum. And kind of, I guess, an important sort of conceptual point is that when this parton acquires momentum, that acquired momentum can sort of allow or induce a gluon radiation sort of from the medium. So this is somehow conceptually a bit different from these kind of vacuum-like splittings that we were talking about earlier, which is actually radiation, which is acquired sort of from the medium. And one of the sort of, I guess, crucial points is that the medium can't kind of resolve this radiation instantaneously. So there's sort of a finite length scale on which you essentially can't tell whether this gluon has been radiated or not. And this length scale is called the formation length of this splitting. So this is kind of some inherent fuzziness in the ability of this radiation to be resolved. And the reason that I kind of want to say this is that it kind of forms sort of conceptually a kind of nice picture of how these the radiation spectrum, or how the energy spectrum of this radiation actually looks like. And the point is that kind of if you have a formation length of this splitting, which is small compared to the mean free path, so that's sort of this picture that I'm showing here on the left, then you essentially have like all of these scatterings occur independently, and they can each independently induce a gluon radiation. And so because these scattering centers also have relatively low, any of these individual scatterings have relatively low momentum, this produces relatively low energy gluons, part of the spectrum, from each of these individual scatterings. But as you go to higher energies, this formation length can get longer than the mean free path. And then you can have many of these scatterings with the medium, which all act coherently. So through that, you can get sort of higher momentum transfer to the medium because all of these scatterings act together and all contribute their sort of momentum to create this gluon radiation. And that gives rise to sort of this kind of what's called, I guess, the LPM regime, which is a characteristically different sort of dependence of the on the gluon radiation energy. And then the other kind of important sort of regime of this radiation spectrum is once the formation length is longer than the length of the plasma, then the entire sort of all of the momentum transfer which you could acquire from the plasma all happens before the medium sort of resolves it. So the basic point, I guess, that I want to make is just that depending on kind of the features of both this radiation and how the parton interacts with the medium, you get kind of characteristically different sort of spectra for the energy of these gluons emitted in this way. So, you know, this is kind of a characteristic feature, I guess, of finite temperature QCD, which we would hope to kind of access, I guess, in jet phenomenology. Are there any points, questions, comments here? Okay, cool. So, okay, now I want to maybe, did someone say something? Sorry. Okay, no. So now I want to make a bit connection sort of to what I was talking about last time, which is to talk about sort of jets in the medium. And so in many ways, I think of nuclei as being very close to being just a bunch of protons. So you can really think of jets to a large degree as being produced kind of in the same way. But these splittings which happen in the jet sort of happen in the presence of the medium. So again, we can kind of think of having, you know, what I talked about last time, that we have these probability, sort of differential probabilities or splitting functions for a parton in QCD to split into two partons as a function of the momentum sharing of those splitties and the angle between them. And it's these kind of successive splittings in QCD which kind of builds up jets. So through, you know, using each of these probability distributions, they tell us, you know, how likely is it that you know, that you get which type of splitting, and what is sort of the angle and momentum of those splittings. And so that builds up kind of the kinematic structure of these jets. And so kind of the types of ideas which I discussed on the last slide are sort of the conceptual kind of underpinning in some way of the statement, which is that these sort of splitting functions will also be modified by the medium. So you can say, like, you know, if you think of it in a classical sense, like each of the legs of these splittings will get sort of some momentum transfer from interactions with the medium. They can have these kind of coherence effects as well, where many interactions with the medium can contribute. But sort of the basic point, I guess, that you need to take away for this talk is just that those interactions with the medium in some way can change these angle, or sort of the probability distributions as a function of these angles and momentum sharing. So by changing these splitting functions in some way through interactions with the medium, you also change the structure of the jets that are produced from those splitting functions, and can try to sort of use that to kind of back out what were these structure of these interactions you had with the medium. Any questions, comments, thoughts?
Yeah, actually, I have a question if you don't mind.
Of course.
So if we think about jet evolution in a time sense, that you have the interaction and then you have subsequent evolution. If we take seriously this idea of what you have in the right-hand picture, where it's splitting and then splitting and splitting, splitting, and these things happen one after the other, then yes, that leads naturally to this idea of the splitting being modified by the presence of the medium. But what I was really deeply surprised by was this paper by Zhongbo Kang and also Xinyan and a couple other folks, where they looked at really the twist 4 contribution to jet broadening. And in really that seemingly rigorous calculation, order by order calculation, then all of the stuff that happens where you have your parton line interacting with things down the bottom in your usual handbag diagram, sort of DIS type way of thinking about the problem, all of the modification that's happening with the presence of a medium is eaten by the PDFs, not by the fragmentation function. And so they have these.
Okay, that's interesting.
Yes, they have these twist 4 PDFs, and it really makes perfect sense in that if you think about it in the DIS picture, that it's all that subsequent evolution where you're talking to, if you're in DIS, the proton, or if you're in quark gluon plasma, talking to the quark gluon plasma, that sort of Wilson line gauge invariant physics goes into the PDF, goes into the starting physics, not the final state physics. So yeah, I guess I don't know if you've heard about that before or thought about it in this context. Yeah.
So I haven't thought about, so that particular paper, I think I'm aware that it happened, but I'm not super familiar with it. So it'd be very interesting to discuss sort of in more detail. So one aspect in which, like, at least what you're saying is interesting, or like a bit different to what I would have thought of, is like, so there was also this paper by Paul Kakal and Al Mueller and Gregory Soyez, I think now a little while ago, maybe 2019 or something, 2019 or 2020. But what they were arguing, I think, is almost the opposite, which is why I would be interested to hear. So their argument, at least as I understand it, is essentially that you can think of, so when you have like this initiating parton is super high virtuality, and then it's splitting sort of to lower and lower virtuality and going closer and closer to the medium scale. And what I think they were basically arguing is that these sort of the formation time or the lifetime of these splittings of very high virtuality is kind of very fast. So in some way it's so fast that you don't have time to really acquire momentum from the medium during that process. So they basically kind of use that to sort of factorize the sort of perturbative QCD, or like PP physics at higher scale. So they say, okay, this like initial part of the vacuum-like radiation happens very fast, and it basically happens as if the medium wasn't there, because it happens so fast that there isn't time for substantial interactions with the medium. And then once it gets to some lower scale, which, okay, they quantify lower in some way, but once only kind of after you've gotten down to some scale, then you have sufficient kind of likelihood of having like medium induced radiation, for example, because you just have these longer formation times, which make it possible to sort of acquire enough momentum during that time. So at least at naive glance, that feels like sort of the opposite thing, which is that rather than taking the medium interactions into the PDF, almost the opposite, that you have like basically jets as produced in vacuum, and then it's only kind of late in some way that you get the sort of substantive part of the medium modification of the spectrum. So I'll definitely, that was kind of the picture in some way that I had just because I was more familiar with those papers, but I'll also take a look at this this work by Zhangbo and Xinyan. It would be interesting to understand like kind of how these two aspects play together.
You guys mind sharing the references that you were just mentioning?
Yeah, we can.
Because there's also some, this is something that I'm trying to look at from a totally different perspective, so maybe.
I mean,
Oh yeah, definitely.
one thing that was very strongly said in the Zhangbo paper was that the fragmentation, the splitting functions associated with the fragmentation functions, or rather the NLO fragmentation functions evolved with vacuum splitting. Like they were very clear about that. But that sort of raises an interesting question for me that I just thought of now, which is when you're doing regular sort of proton physics DIS, the PDF splitting functions and the fragmentation function splitting functions are the same. And so is there some deep reason why those are the same, or is that an accident? And if there's a deep reason why they're the same, should there also be some kind of symmetry happening in heavy ion collisions?
So I guess that would be the question of whether the so if the fragmentation function, like if nothing about the final state interactions modifies the fragmentation functions, then I guess you would just use sort of perturbative QCD splitting functions both for, or use perturbative QCD, I guess, both to describe the evolution of the like the evolution of like PDFs, for example. How do you get out the quarks and gluons from the proton, whatever. Of course, you would use perturbative QCD for that. You would also use perturbative QCD for the fragmentation functions, and you're happy. I don't know how much work, maybe one of you guys knows better. I mean, I know that they've tried to constrain, of course, like fragmentation functions in heavy ion collisions, but I guess they're still based on PQCD evolution. That I'm actually not sure about.
I mean, all of this is PQCD. I think the question is whether it's PQCD in vacuum or PQCD modified.
Yeah, but for like the fragmentation functions, so I know that there's like fits of where they try to extract, like, I think that there's fits for hadron fragmentation functions in medium, although now that I've said that, I'm not actually positive that that's true.
And you still can modify propagation, right? Even if you don't fit into the splitting yourself. Those are two different variables.
Yeah, I guess so. That is true. So I guess the fragmentation functions only also impact. Like, I wonder if you should think about the fragmentation functions as still being like, because you kind of have the medium, and then it's sort of, I guess, at the end where you would think of the hadron fragmentation functions as telling you how to kind of turn all of these partons back into hadrons. And so maybe it's like, okay, you should medium modify these splittings of like as the shower develops. But I would have to think, I'm not sure if it's obvious whether you should medium modify the hadron fragmentation function, since I guess it's at the kind of phase transition where everything is turning back into hadrons anyway. But I'm not, yeah, I don't know about that.
I don't think we'll resolve this right now. But thank you.
At least not before two.
Right, exactly, before ESCOM turns us off. Yeah, so thank you. And maybe we can continue this discussion via email.
Yeah, that'd be very interesting, and share references as well.
Absolutely. Super, thank you.
Awesome. Sorry, are there any other questions before I go on? Okay, cool. So what I sort of told you about last time is that, of course, these different types of splittings also produce different types of jets. So it's kind of crucial that these splitting functions for different types of partons are different, like they have different probabilities, different angular and momentum scales. And so like one of the sort of example that I gave last time is that, if the initial splitting in a jet is a gluon to two gluons, then these are typically wider because this typically happens at larger angles and there's more radiation and stuff like that. Well, if you have a quark splitting to a quark and a gluon, the kind of characteristic features of this radiation are typically narrower. And so the only sort of reason, I guess, that this is important is just sort of the conceptual idea that you can look at jets and try to access in some way what are the splittings that actually happened because of the imprint that those splittings leaves on the structure of a jet. And this will be important kind of for what I want to talk about today, which is this particular splitting where you have a gluon that splits to two quarks. I'll try to tell you sort of why that's interesting, but these are essentially the three types of QCD splittings that you can have. And so kind of today I'm going to sort of focus on the phenomenology of medium modifying this particular splitting, which is the gluon splitting to two quarks. Make sense so far? Cool. So this is maybe a bit of a jump, but one of the, so I said that we want to study gluon splitting to quarks. And actually specifically what I'm going to be talking about is gluon splitting to charm quarks. And the reason for that is essentially sort of experimental or phenomenological, which is that the charm is too heavy to be produced in hadronization. So in general, it's very hard to tell whether you had a gluon splitting to two quarks. But if you have a gluon splitting to two charm quarks, then actually it's easy because you can see essentially because you can't produce the charm quark in hadronization by itself, if you find hadrons containing charm in your jet, then you know that there was a charm quark in the shower because you can't have produced those hadrons in any other way. And so this is kind of the basis to say that if you find a jet which contains two d mesons, then actually we sort of studied this. This means with very high purity, you had a gluon splitting to two charm quarks inside the shower. And the way that you access it sort of experimentally is through these d mesons. And I guess maybe the point, at least to connect back to studying this gluon splitting to light quarks, is that actually the charm quark is not that heavy. So okay, I just said it was heavy because you had to produce these d mesons, but if you look at very high energy jets that are much higher than the charm quark mass, you can also use this gluon splitting to charm quarks to study essentially gluon splitting to light quarks, because at very high gluon energies, you can kind of neglect the charm mass, besides that it's sort of important for this experimental signature. So I feel like that was maybe a bit much, but the point is just that there's a way to access these gluon splitting to charm quark sort of in jets with high purity. And so that gives us sort of a good way to sort of tag this splitting sort of more experimentally. And then I'm not really going to talk about the details, but you can kind of compute the medium modification of this splitting and then try to kind of compare essentially jets with two d mesons in heavy ion collisions to jets with two d mesons in proton-proton collisions. So that's kind of the conceptual idea. Does that make sense at this level? Cool. So essentially we had a paper relatively recently where we computed the modification of this splitting function of gluon to charm quarks. And so what I kind of mean by that on sort of the level that we've been talking about here is that sort of these interactions with the medium change how this splitting probability well, yeah, changes this splitting probability as a function of kind of the relative transverse momentum of this CNC bar pair, here called Kc, which earlier I was calling just an angle, and the momentum sharing fraction of this CNC bar pair. And for reasons that I'll kind of discuss a little bit later, how these probabilities change also depends on the energy of the gluon, which I'll call Eg. So the details of how this is done, I don't want to go into, but I want to kind of discuss sort of what are the interesting features of this modification and how you might be able to access, sort of use this type of process to access these features in phenomenology. So the simplest kind of signature, which I also discussed earlier, is that if you have these, so you've produced a pair of charm quarks from this splitting, and then they're undergoing interactions with the medium that are broadening sort of their relative momentum. So on average, because of this sort of Brownian motion that they're going through with the medium, the relative momentum, which here we're calling Kc, is getting larger. So if you think about this as a probability distribution, you know, already in perturbative QCD, you had some probability distribution for how charm quarks are produced as a function of this angle or relative momentum. And in the presence of a medium, on average, this angle gets larger. So you can think of this as sort of a depletion of these very of these charm quark pairs, which have very low relative transverse momentum because they're kind of broadened by the medium. Does that make sense? So this is kind of one of the, oh yeah, go ahead, please.
Sorry, just to check I understand. When you say depletion, you mean that the medium is causing these things to split apart. It's not that there's a lower probability they start at smaller angles. Is it that as they evolve, they get kicks from the medium that cause them to split?
Yeah, exactly. So it's just that if they were produced with small Kc originally, interactions with the medium kind of tend to push them apart. And so if you sort of measure Kc, I guess, after medium modification, you'll just find that it's generally at larger angles because of these interactions.
Okay, that makes sense. Thank you.
And so this is kind of, this broadening is sort of a characteristic feature of these medium modifications. And I think that this particular process might be a clean way to access it sort of experimentally. But I'm going to put that aside a little bit to talk about two, I think, slightly more exciting or more novel sort of features of this gluon to CC bar splitting function. So one of the things which we sort of found is that there's less modification of the splitting function if you increase the gluon energy. And I'm going to go on to this on the next slide, so you don't necessarily have to understand it in detail here. But this is really a signature of what we call the formation time of this gluon. So essentially its lifetime in the medium sort of gives you have direct access in some way to the lifetime of this gluon through the modification of the CC bar pair. So I'll tell you more about that on the next slide. And I think it's a pretty cool possibility for future phenomenology of this process. And then the final kind of thing, which I'll also talk about on the next slide, is that we found a medium enhanced rate of CC bar production. And conceptually, the point is essentially that interactions with this gluon, so there's some mass threshold. So because charm quarks have mass, the gluon can't just split to two charm quarks unless it has enough virtuality to sort of produce the mass of the charm anti-charm pair. And so one thing, at least, which was quite surprising to us, is that you can actually have interactions with this gluon that enable the gluon to split to a CC bar pair when it wouldn't have otherwise. So I think, at least morally or kind of conceptually, you can kind of think of this as a gluon which didn't have sufficient virtuality to produce a charm quark pair, which can be promoted above threshold through interactions with the medium. And what's quite cool about this is that it predicts sort of a rate increase of charm quark production sort of from interactions with the medium. So both of these last 2 points I'll discuss in more detail on the next 2 slides, and then kind of wrap up. All right. And these, I think, are kind of I think they're quite new feature of this splitting function, although it's probably a feature of other splitting functions, but maybe have unique kind of phenomenological access in this process. Okay, so I want to talk a little bit more detail about each of these individually. Are there any questions before I go on? All right. So one of the things which I kind of alluded to a little bit earlier is that gluons have sort of a lifetime or a formation time, which depends on their energy, e.g., and also on their virtuality. So you can kind of think in some way of the kinematics of the gluon, so both its invariant mass and its energy is really sort of telling you how long it will live in the medium. So in this kind of little cartoon diagram, you can sort of imagine that this gluon is produced, and somehow it's going through the medium, and at some point it will split to charm quark pairs, or to a charm quark pair. And the amount of time that it takes for that splitting kind of to happen is this formation time, which you can control through the kinematics of the gluon. And what I think is quite cool about this gluon splitting process is that actually sort of we kind of have access then by changing this gluon energy and changing the virtuality. You can really also change the sort of lifetime of the gluon on scales which are relevant to the quark gluon plasma. So the idea is kind of, if you have very short gluon lifetime, then this charm quark pair will spend most of the lifetime of the medium. The system will be 2 charm quarks. And so then the modification is characteristic of the modification of charm quarks. On the other hand, as you have longer and longer gluon lifetimes, then the modification of this process becomes more and more dominated by sort of, I guess, interactions with the gluon. And then, for example, signatures of broadening, which you might expect on the charm quark pairs, will be much less in this case, just because the charm quarks were not in the medium for very long because the gluon was there for so long. Does that kind of conceptually make sense? So by changing the kinematics of the gluon, we can also change its lifetime. And that changes how this process is modified. So what this means is that if you look at the signatures of broadening of the charm quark pair for very high gluon energies, it's less. And the reason that we give to that is that this gluon lifetime is longer.
Wouldn't we expect Q to be on the order of EG?
Yeah, so this is actually, very good point. So yeah, essentially the problem, so this was sort of one of the main ideas why we started looking at gluon splitting to charm quarks, is that in a jet, in principle, if you have a jet whose first splitting was this gluon to charm quarks, then the invariant mass of the jet is basically this virtuality. So you can access Q through the jet invariant mass, and you can access EG through the jet energy. So in some way, we thought you should be able to isolate sort of particular gluon lifetime by sort of changing the kinematic. So it's exactly the case that in general, the invariant mass and the energy will go together. So like that they'll get larger together, but we thought, okay, then you can just look at the set of, you can look at the part of phase space where you have, for example, high gluon energy and low invariant mass, which isn't as probable, but it is sort of accessible. The problem with that is that, if you want to look at we want to find like different broadening of the charm quark depending on the formation time. But the KT, so like the opening angle of charm quarks already in vacuum changes a lot, especially if you're messing around with the ratio of EG and the invariant mass of the jet, then the kind of baseline, so like what is just the opening angle in vacuum, is also changing a lot. So in order, it's kind of still, I guess, work in progress, which is something that I am working on / interested in quite a bit, is how do you quantify, like with this very changing baseline, can we actually show that the broadening is different or not? I don't know if I feel like that was not a very good explanation. Did that kind of clarify your question, or?
Yeah, basically everything depends on everything, and you're hoping that you'll be able to tease something out of this chaos.
Yeah. So you can definitely change the formation time. That's not difficult. But yeah, then what is hard is to show that the broadening is actually different for different formation times, given the fact that the baseline expectation for the opening angle is also different, I guess. Yeah, so pretty much exactly what you said. You change something and everything changes, and then you have to try to tease out this not enormous effect of formation time dependent broadening.
And I'm guessing that your understanding of everything changing when everything is based on something like Pythia?
Yeah. Yeah, so we were mostly, at least when we were doing this, when we were kind of studying this part of the problem, which actually hasn't resulted in a publication yet for basically the reason that you were pointing out. Yeah, we're studying essentially take Pythia, and then modify somehow the splitting probabilities, and pretty much any way that you do it. Yeah, you can already in Pythia, if you change the formation time, you'll change the distribution of opening angle a lot, and the amount that you change it just in Pythia is comparable or larger to the amount that we would expect it to be changed by broadening. So you have to do something more clever to really try to tease out these two effects. But conceptually it's there, but then, yeah, conceptually this effect is there and I think is really cool. So I'm pretty excited about it, but yeah, then to actually do it is more challenging. So work in progress.
Super, thank you.
Yeah. Any other questions about this sort of gluon lifetime picture here? Cool. Okay, then I'll just, all right, well, we're 10 minutes until the lights go out, so good timing.
Exactly.
Yeah, so just as kind of a side comment, one of the reasons that we're actually specifically interested in gluon splitting to charm quarks rather than like to bottom quarks, for example, which are also heavy, is that actually you can get a sort of delay of this process from the formation time for kind of reasonable kinematics at the LHC, which would provide a pretty substantial delay in terms of the total evolution of the quark-gluon plasma. So this might be a way to kind of really try to access different sort of time regimes of the quark-gluon plasma as well in sort of upcoming measurements. But as Will unfortunately already opened the bag, it's also not so easy. Okay, so what is a bit easier, and actually, so we just put a paper on archive yesterday, or appeared on archive yesterday, is on this sort of other unique part of this CC bar phenomenology, which is the medium enhanced rate of CC bar production. So what I was kind of telling you about earlier is that you can look at jets with two D mesons inside of them. And this tells you with high purity in Pythia, at least, that you had a gluon splitting to charm quarks somewhere in the shower. And so by kind of looking at these, this type of jets in proton-proton collisions and in heavy ion collisions, we can try to access the rate of this gluon splitting to charm quarks. And what we found in our calculation was that this rate is enhanced due to interactions with the medium, and kind of the point I was trying to sorry, go ahead.
I think that was background noise. Please go ahead.
Okay. Yeah, so we found in the calculation of this gluon to CC bar splitting function that this rate is actually enhanced. And then we use this splitting function sort of along with Pythia to estimate the size of this enhancement on the number of DD bar tagged jets, which could be measured in heavy ion collisions. So the idea is that by kind of looking at the ratio of the number of DD bar tag jets compared to the number of jets in proton-proton collisions and in heavy ion collisions, that you can try to access this enhancement of the CC bar pair production. And using the calculation of this medium modified splitting function, we sort of estimated the size of this enhancement. So here in blue, what you're seeing is the sort of Pythia rate of jets with a DD bar pair compared to the number of all jets produced. So this we can think of as the proton-proton baseline. And then due to these interactions with the medium, we expect the increase with respect to this proton-proton baseline, which is given by this red band in heavy ion collisions. So what I think would be quite kind of cool feature of this is that if you could measure an increased rate of DD bar jets, or if you can measure sort of the rate of DD bar jets in proton-proton and in heavy ion collisions, we kind of argue and I think show that this rate enhancement can really give you access to this kind of feature of the splitting function. So this sort of medium-induced creation of CC bar pairs. So I think that would be a pretty cool opportunity to kind of see this unique feature of the splitting function modification kind of in phenomenology through this ratio of the rates of different types of jets. Does this make sense here? Yeah, please.
I think I understand the usefulness, but I don't think I'm fully understanding why the medium is enhancing CC bar. Is there sort of a simple reason, or is it quite technical?
Yeah. So I think sorry, go ahead.
Also from my end, right? I mean, you were saying it lifts up the energy, but why is this one way, right? why doesn't it also take it away? And what, so why is there bias in the direction of lifting it up?
Yeah.
Yeah, that's also a good point. So, right. So I think conceptually, so at least the way that I would, let's see how best to explain it. So I think the issue is kind of that it's, so you have this threshold. So, you know, in PP, say maybe you have like some jets which would produce, you have some gluons which would produce a CC bar pair in vacuum. I think, okay, so then through interactions with the medium, sort of, I guess, what we checked in the calculation, I don't know that I would say that we maybe conceptually fully understand why does it happen. But in the medium, you can have gluons which wouldn't have split to a CC bar pair in vacuum that can split to a CC bar pair. So that we checked, and we kind of give it the interpretation of modification of the gluon, although I would say that interpretation we can't check. We can just say some gluons that wouldn't have split now will. And then I think your question is also very good, is what about the gluons which would have split in vacuum that won't?
Yeah.
And I think this is also sorry?
It's always the steeply falling spectrum, right? You've got
Yeah.
way more
Yeah.
soft stuff than hard stuff. So you're going to get a bias towards kicking things up.
Yeah, so I think that might be, yeah, I think that might be the kind of, I guess maybe that could be the underlying reason it works. So I will say that we first kind of wrote this paper and we're quite excited about it already, probably 6 months or even more ago, I forget exactly when. And then people basically said what you just said, which is like, okay, how do you really estimate in a consistent way what will be the effect of the modification of other splitting functions and other, like, so essentially, why do you think that jet energy loss, for example, like, won't modify also this distribution? And so we essentially went through 6 months of like writing a little toy parton shower where we modify all of these splitting functions, or also modify glue to glue glue and quark to quark glue to try to estimate kind of the impact of these modifications on the gluons that could split to CC bar pairs. So that's to try to address the question of like, okay, what else could happen to that gluon where it didn't end up splitting to a CC bar pair? And happily, what we actually found at the end of that exercise is that this particular ratio, so if you do really look at the number of DD bar jets to the number of jets, and then you take the ratio of this between proton-proton and heavy ion collisions, actually it's maybe even surprisingly direct access to just this sort of gluon to CC bar, and we're sort of, at least it was not obvious that we would be so insensitive to also the modification of these other splitting functions like glue to glue glue and quark to quark glue. So that was kind of and conceptually it might be what Will was pointing out, that you are kind of on a steeply falling spectrum that I would have to think about, but it was something we kind of checked in a fair amount of detail, that this sort of ratio actually gives you access just to this modification of the glue to CC bar splitting, and that you don't have to worry so much about the modification of all the other splitting functions that could take your gluon and make it so that it doesn't split to a CC bar pair in medium. So I think it's a kind of intricate question, which we took a while to kind of try to give a quantitative answer to.
Okay, thank you.
Cool. Any other questions?
You're on borrowed time.
Yeah. We're looking at the
Yeah.
clock.
Oh, yeah, it's 2:02. All right, cool. I told you about some cool phenomenology of glue to CC bar and some aspects of this that we're either have explored or are excited about exploring soon. So with that, maybe I should wrap up before the universe wraps up for me.
Yeah. So yeah, why don't we just, because in the interest of time and SCOM, thank you so much. This was really great, really good physics, and thank you for talking to us. And I'm sure we'll have more questions by email. But yeah, thank you very much for the time.
Yeah, thank you so much for having me and for all of the good questions and a nice discussion and everything. So it's very enjoyable.
It was fun.
Yeah,
Honestly.
super.
Good fun.
All right.
And
Take
safe
care,
travels.
guys.
Bye.
Thank you. Bye.